We often have guest speakers from universities come and talking about astrophysics, cosmology, and as the new president, I realised that we haven't asked Ross, being head of the cosmology and astrophysics, if he wanted to do a talk about it. So instead of asking him to congratulate the speaker at the end, I invited him to do a talk, and he's going to talk tonight about the edge of the universe. So, no further ado, I'll swap over to Ross.
Okay, I'll start by asking a question. When we look at the night sky, what do we see? Typical view, there's a facts and things in there, but basically, I guess as astronomers, you're all looking up and seeing stars. Well, the exception, one or two exceptions. Basically, we're looking at everything we're looking at there is within our galaxy. And the few exceptions, of course, the clouds and Magellan, which are part of our local group. So everything we see with our naked eye is quite close to us. The galaxy is a very large place, but the universe is bigger than we. The telescopes we see further. The one on the left there is the telescope that's used for the Sloan Digital Sky Survey, and the one on the right is the UK Split Telescope up at Coonabarabran. Both of these have done some excellent survey work. The biggest sky survey is the Sloan Digital Sky Survey. The spectra of something like 2 billion stars have been measured to a distance of about 2 billion light years. Now 2 billion light years sounds a long way. Okay, that's the summary of the work they did. Now I haven't looked at the whole thing, but they've done a couple of slices. Here and done some very detailed work within that, but there's certainly a lot of stars and all of that. Each point in this picture is a galaxy containing about 100 billion stars. The Earth is in the centre of this. Okay, now what's the most distant object you can see in the universe? And when I say see, I use that in a more general sense, because obviously this object is in the microwave. It's of course the cosmic microwave background radiation. That's the furthest we can observe by any means known to us today. Okay, and it's got a redshift of 1089, which corresponds to an age of 379 after the Big Bang at a distance of about 46 billion light years. It consists of remnant radiation emitted when the first hydrogen atom first hydrogen atoms formed, I should say, and a temperature of about 3,000 degrees, and it's been redshifted down to about 2.7 above absolute zero. It's uniform to 1 part per 100,000. Okay, now we're going to draw the universe. And that red circle there is the cosmic microwave background radiation. Okay, and then go to the Sloan Digital Sky Survey. Small little blue dot in the middle. About 2 billion light years. That represents 0.01% of the universe. So what we're really going to talk about is the other 99.9%. So the bit you're familiar with is 0.01%. and in fact less than that. Now, there's a lot similar about the different parts of the universe, all the same. It's quite a sobering thought when you actually do the numbers. Okay, we're going to look at what lies outside the cosmic microwave background, and then look at the look after the immediately after the cosmic microwave background and when the first stars and the first galaxies formed. And finally, we sort of have a look at what's coming up to give us more of an idea about it. Alright. Okay. What happened before the cosmic microwave background radiation? Well, everything we know about it is based on the observations made of the actual cosmic microwave background radiation. Observations made after the thing, so looking at events that have happened since that time. And the other thing is physics experiments on Earth, such as the Large Hadron, some of the large colliders, like the Large Hadron Collider. Essentially, those experiments are used to extrapolate back from the cosmic microwave background radiation. Okay. The one thing about the cosmic microwave is that it's extremely uniform to one part in 100,000, and that was extremely difficult to explain when they first realised that. And the more they've studied, the more they found that they've confirmed that it's so uniform. One of the theories that was proposed to explain that was a theory called inflation, and was first proposed in 1980 by Alan Guth, who was a theorist working on a similar problem, and he realised he'd come across a mechanism where it was physically possible for the universe to expand enormously in a very short space of time, and the numbers involved are so incredible I can't really get my head around it. But essentially, this extraordinary expansion took an object that was the size of a ball or a pea or something like that, and took it out to the realms of what we now see as the edge of the universe. And that all happened in an incredibly small period of time, 10 to the minus 37 seconds. Just getting your head around that's incredible. But this was proposed in 1980, and it's still considered the principal theory in regard to why the cosmic microwave is so uniform. That's a picture of Alan there. Incidentally, one anecdote I heard recently is that Alan actually, when he proposed it, he thought the theory would last 6 months and get shot down, and he's been dining out on it ever since. But interestingly as well, certainly inflation is able to explain the uniformity, but it puts some very specific initial conditions on the Big Bang, and that is a concern to a number of scientists, and included in that is Sir Roger Penrose, who actually is strongly in favour of inflation not being needed, but he also argues that in fact the initial conditions that we needed to get inflation are actually so unlikely that it probably never happened. What I don't understand is exactly how he gets the smoothing without it. He's written a book on it, but it's very hard read. That's Sir Roger there. Okay, so immediately after the period we believe inflation was, the temperature of the universe is 10 to the 28th degrees. So that's 1 followed by 28 zeros degrees. Doesn't matter whether you measure it in Kelvin, centigrade, Fahrenheit or whatever, it's very hot. fact, the conditions of this time are so unfamiliar to us that it's not really. The universe really doesn't resemble anything that would seem familiar to us. The universe contains only massless particles, and these are different to everything that's currently in the universe now. Okay, so I'm going to move on to about 1/10 of a microsecond after the Big Bang, and the temperature now is comparatively cool, 10 to the 13 degrees. This particular point is actually very similar to what they're producing in experiments with the Large Hadron Collider today. So that's really the first time we're actually able to even see anything that vaguely resembles what the universe was like at that time. We now have something that's familiar to us. Some of the particles we've come to know from the particles experiments have suddenly appeared now, and some of the common forces that we know as well are around. The main particle at this time is quarks. The universe is still far too hot for even things like protons and neutrons to form. Okay, we get to about 1/10 of a millisecond. It's dropped to about 2 by 10 to the 12 degrees, and then quarks now are able to cool, and to such an extent that protons and neutrons are able to form, and these become the main form of mass at this time. It reaches about a second in age. Neutrinos, which have been operating freely, or been interacting with the other particles, stop interacting, and these actually move freely through the universe without interacting with, or only occasionally interacting with other matter. For those who know a little bit about neutrinos, for example, we've got neutrino detectors on Earth. They're usually an enormous hole in the ground. It's usually underground in an old mine or something, and it's usually something in the order of thousands of square metres in volume, and containing pure water or dry cleaning fluid or something like that. And they reckon they're lucky if they get 5 neutrinos colliding with these billions and billions and billions and billions of molecules of water in a year. That's how unlikely they are. There's hundreds of thousands of them going through your body as we speak. Okay, and when the universe reaches 1,000 seconds in age, temperature's now dropped down to 1 million degrees, and for the first time we actually start to get atomic nuclei forming. And in fact, in the first 1,000 seconds of the universe, all the original formation of helium is basically occurs. Obviously, the subsequent helium in star formation, but there's an awful lot of helium that's formed in this first 1,000 seconds. Then after that, after that it stops. So the universe cools too much now, and it's not able to now produce any more nuclei, and it won't produce any more nuclei now until stars occur, and that's quite a while off. At this time, all the matter in the universe is in a plasma form, which basically means that you've got positively charged nuclei, you've got protons, which are hydrogen, you've got helium, and then you've also got negatively charged electrons. And we have a plasma around today. If you heat up gas enough, you'll actually separate the electrons off the nuclei, and you'll get a plasma. But obviously, in the early universe, everything was a plasma. One of the things about being a plasma is that the photons interact with the positive and the negative particles, and they're very strongly bound in that situation. And basically, it means that the universe at this time is opaque, which means that light can't freely move through it. Any photons that we did try to move through it would get scattered very quickly by the charged particles. As the universe expands, it's cooling all the time, and eventually, as it cools, some of the electrons are able to form stable orbits around the positive nuclei, and you start getting neutral atoms forming. First event to happen is after about 15,000 years. Helium absorbs one electron. After 100,000 years, it captures a second electron and becomes neutral. But helium is only a minor player at this stage. The major one is hydrogen. And at 379,000 years, it's cooled to a temperature of about 3,000 degrees, and electrons now are able to form stable orbits around the protons to form neutral hydrogen. And as I said, when it was plasma, the photons couldn't travel very far without running into something that was charged. All of a sudden, all the charges have been balanced out. All the electrons are now going around a positively charged nuclei, and suddenly the photons are released and are able to travel without interruption, without being scattered. And this event, now when you sort of read about this, sometimes you think, oh, it sort of happened overnight, but in fact it probably happened. It probably took several hundred years for it actually to play out completely, maybe even 1,000 years. But certainly it happened, in the scheme of things, it happened reasonably quickly, but it certainly didn't happen in minutes or hours or days, certainly many years. But fairly quickly it went from being very, very highly charged to being neutral without and from light terms it went from being opaque to being transparent. Okay. One of the terms for the cosmic microwave background radiation is also referred to as the surface of last scattering, and you probably see where that name comes from. Okay, when we look at the cosmic microwave today, what we are seeing are photons that are released back 13.8 billion years ago and have been travelling through free space uninterrupted for 13.8 billion years. Okay, so they're bound into atoms, and all of a sudden they break free and they keep going. Now, not all of them, of course, have survived. Some of them have run into other planets and stars along the way, but a lot of them have obviously got through. Otherwise, we wouldn't be able to see it. Okay. The other thing to remember as well, when we look at the cosmic microwave, is that we're seeing an event that finished 13.8 billion years ago. It's not out there now. We're able to see that event now today because of the size of the universe, but we're actually looking at something that happened 13.8 billion years ago. And as I said, the light's been travelling for 13.8 billion years to get to us. Another thing to remember is when we look at it today, the light that we see today has been travelling 1 day longer than the light we saw yesterday. So we're not seeing the same thing over and over again. We're actually seeing a slightly different point, a bit further away each day. It looks the same. Okay, we've come back in a year later, maybe the patterns have moved a little bit, I'm not too sure, but certainly we're not seeing the same thing each day. We're actually seeing light that's going a bit further. So the light we saw yesterday has gone 1 day past us. If it didn't hit us, it's gone past us. Or if it hit us, in fact the one closest up we see is actually been absorbed by our eye, hasn't it, by our camera. Okay, and the place where that light has come from is now 46 billion light years from Earth. That's pretty staggering in itself. Okay, and you're probably quickly doing the maths and saying 13.8 from 46 doesn't add up. Well, we all learned that Einstein told us that nothing moves faster than the speed of light. Well, it turns out that space moves faster than the speed of light. Space itself can expand faster than the speed of light. In fact, in the area of the cosmic microwave background radiation, it's actually going at some 1,000 times the speed of light. It's really moving away from us at a great rate. But the light has moved through space at the speed of light for 13.8 billion years, but because of stretching, it's now 46 billion. That space is now 46 billion light years away from us. Okay, can we see anything before the cosmic microwave? Not at present. There's no known instrument we have that will see it, but there are some possibilities. And when and where remains to be seen. Two of the possibilities are what I mentioned briefly before. The first is the formation of helium-1+, which is where it captures its first electron, and neutral helium, where it captures its second electron. Both of those events would have emitted radiation, which is on a different wavelength to the hydrogen wavelength, and there are suggestions that they may be able to be seen through the cosmic microwave background. Another event, and this happens about 1 to 2 seconds after the Big Bang, is, we said, the decoupling of neutrinos. This is where prior to that, neutrinos are actually trapped like the photons were. And the neutrinos are then able to travel freely through matter with most of them getting absorbed. And this event is referred to as the cosmic neutrino background, and it would have a redshift of something like 10 to the 10. So remember, cosmic microwave with a redshift of just over 1,000. Well, this has got a redshift of about 10 to the 10. This again is another event. If we can build a successful neutrino telescope, which is a challenge in itself. That is a possible event to observe, and will give us a snapshot of what the universe was like a second after the Big Bang, and that will look vastly different to what we see with the current cosmic microwave. And the other event, it really just immediately after when inflation is supposed to have occurred, when gravity first separated out from the other forces, is an event they refer to as the cosmic gravitational wave background, and that would have a redshift of 10 to the 25, and that would actually give us a clue as to, a much bigger clue again to what the Big Bang might have been like. But again, you have to build a gravity detector, and we haven't detected one gravity wave yet. At least we've detected a few neutrinos. But they're challenges for the future, and I guess the fact that we can observe as much as we can today means that perhaps some of these things are not impossible for future generations. Okay. Is there an edge to the universe? Certainly the cosmic microwave background radiation isn't the end of the universe. As we've seen, there are events outside that, even though it does stop us from looking beyond it. But there is actually a point beyond which we can't communicate with. And we refer to this as called the cosmic horizon, and everything inside that we call the observable universe. Outside that, we believe that space continues, but we have no way of ever knowing that. There's no way of communicating beyond that cosmic horizon. This space is considered to be other universes. At Glasgow, I talked briefly about multiple universes, and this is really the first type of multiple universe is what's outside the space that we actually get involved with. Okay, I'll just show you a little thing here. Okay. Does the universe stop at the cosmic horizon? Okay, so this is notice it says 42 billion light years, so there are different, you find with a lot of these numbers that there are different versions of the numbers, and some people quote 46, some people quote 42. I believe 46 is the more recent one, but I guess it's pretty academic anyway. No one's going to get that far anyway.
Everybody who reads anything has to talk to the
Who's the answer? Well, Douglas Adams. Anyway, okay, so this is one possibility. One possibility is that everything stops at the cosmic horizon and we just fall off the edge. But I don't think that's the case. I reckon it probably continues. And I refer to, this is my term, but I refer to it as the greater universe of everything, everything including our bit plus beyond. So this is the case here. So this white circle is our universe. There we go. This white circle is our universe. We're here, in the middle of that. So this is our 42 or 46, whatever you agree on. But all these other red circles can be considered universes in their own right. And somebody in the middle of this universe can't talk to us and we can't talk to them. In fact, they can't even talk to anything in our universe. Okay. The universes, they don't necessarily have to be stacked up together like oranges or something. They can also overlap. And in this case, again, the white circle is us with the little white star in the middle is where we are. And we've got the red circles again. But I've drawn a blue circle here, and the blue circle overlaps with several universes. Someone in the centre of the blue universe, which is that blue star there, it's still outside our universe, but they would look at part of our universe and actually see it as part of the universe. And if they're a bit closer, they would, in fact, if that blue circle was closer, so that actually went around us, we'd actually be able to share part of the universe and even communicate with each other. Of course, they would then be inside our universe. When I say communicate, of course, over those distances, it's one signal going out and that's it, I think. And it's a long time before anyone gets it. But all the same, the principle basically is with the cosmic horizon is that anything outside that, it's impossible because it takes longer than the age of the universe as it is. So in that sense, the actual title is actually a bit of an oxymoron, really, because there really isn't an edge of the universe. But it's a catchy title, I guess, so that's why I chose it. Okay, after the cosmic microwave finished, You've got a nice warm universe. It's full of hydrogen and helium, which are neutral. It's still uniform in temperature, at least for a few years, and nothing much is happening. All the matter is neutral. There are no sources of radiation, or are there? Hydrogen consists of two particles, a proton and an electron. We'll concentrate just on hydrogen for this example, but it's true of other things as well. Both of these particles have a spin. In quantum mechanics, the spin of a particle comes only in fixed amounts, so you have a spin of a half. In fact, both proton and electron have a spin of a half, and it's either spin up, or spin down, or spin plus, or spin minus, and it's only one or the other. Okay, so this is our hydrogen atom, and we've got a blue proton in the centre and a red electron going around there. And this drawing, we've got the spins are pointing in the same direction. The other possibility is that the spins are pointing in the opposite direction, which is said to be anti-parallel. I don't have a diagram for that, but you can pretty much imagine it. They're not always, the spins basically only point the same direction, either up or down. Obviously, a similar case would be with both arrows pointing down, but that would still be parallel. It's only when they're pointing in opposite directions that they're anti-parallel. When the spins are aligned, in other words, if they're parallel, then the electron has slightly higher energy. And the spin of either particle can flip, and when it flips, it emits a weak microwave signal. And that signal is detectable. And that can actually form the basis of making measurements of the distribution of gas during the dark era. So even though it's not giving off, there's no bright light sources shedding light right across the universe, you can still see something going on there. It's difficult to do, and I don't believe they've actually made any good measurements yet, but it's an error again that people are talking about observing. And this will help to fill in the gap between the cosmic microwave, which we can see very well, and what happened in the first stars. Okay, so what happens during the Dark Ages is quite a big change occurs. It's said that the cosmic microwave very, very uniform in terms of density, and all of a sudden, when the first stars appear, matter appears very clumped. The clumping, it's certainly not as clumped as matter is today, but it's certainly approaching that very quickly. So in a relatively short period of time, matter's gone from being very uniformly spread to being significantly clumped. And without being able to look at that microwave thing, we can't really see exactly how quickly this has occurred. And this raises some very, very interesting questions for those who are trying to understand exactly how these first stars formed. The current estimate at the moment seems to be that the first stars formed about 150 million years after the Big Bang. So if you remember, it was about 379,000 years was the cosmic microwave. So it's several thousand times on in the time span, of course, before we start to see stars. Now, we know the composition of the universe at this stage, and in fact, there's really only two principal elements that are available to us, hydrogen and helium, and they've got a ratio of 3 to 1 by mass, or if you actually count for the fact that helium is 4 times heavier, it's actually 12 to 1 by actual count. But that's what's called primordial matter. So in other words, it's what was formed in the original formation event. We haven't yet seen these early stars, but there's been a lot of attempts to actually model what these stars may have been like. There have been early theories on star formation that suggested that in fact the stars of 300 solar masses were impossible, but more recent work has shown that in fact that they are possible to form, and you need at least about 300 solar masses to actually get this hydrogen and helium mixture to actually form a star. And they burn extremely quickly. The bigger the solar mass, the faster it burns. And the bigger it gets, the faster it burns. And that's an absolute rule. Some of the brightest stars in our area of the thing are 20, 30, 50 solar masses, something like that. And they burn extremely brightly and burn up in a million years. Some of these might even last a million years at 300 solar masses. I'm not sure the exact time scale, but certainly much faster than our sun is burning. So form fairly quickly, and they'll go supernova within a relatively short space of time as well. After they go supernova, in that event, it synthesises pretty much everything we know, everything in the periodic table we know about. So all the elements we're familiar with basically are produced within these stars and gets pushed out into space when the supernova occurs. Okay. So they haven't actually been observed yet, but they have been predicted by computer simulations.
If they're that big and they're very that fast, they could be observed?
Oh, yeah, they could be observed. They're still around for millions of years, so the possibility of observing them, they're so far away that essentially they're still quite faint. We observing galaxies not long after that. Some of the big telescopes on the horizon, it's possible that some of the bigger early stars will be possible to observe. I'm not too sure what's the lunar-sized telescope to actually observe them. But I'm sure there's people out there keen to try and do it. And certainly they're very bright. There's no doubt about that. In fact, they're probably that bright. They're probably in ultraviolet rather than visible light. Some of the earliest light sources we see are quasars, and of course the quasars are most likely to be remnants of these first supernova. And the light from these quasars shows evidence of being absorbed by heavy elements. So that's first indirect evidence to indicate, in fact the quasars themselves are evidence that there's been early star formation, and the absorption of light by heavy elements immediately around them is a further clue. And for each time a supernova goes off, of course, it enriches the immediate surrounds with heavy elements, and those heavy elements get mixed in with the hydrogen and helium mixture and form the basis of subsequent star formation. So subsequent stars are smaller in size because if you've got some of these heavier elements like carbon and oxygen and silicon and so forth, they will burn at much smaller sizes. And of course, for example, our sun There's only one solar mass, and it was able to get going quite well on its own. Obviously, it's got enough of these heavier elements to kick it off. In fact, even dwarf stars, of course, can still get going if there's enough heavy elements around. Okay, earliest galaxies. This is a shot that was taken last year by Hubble. It's called the Hubble Extreme Deep Field. So the earliest galaxies known to exist are about 500 million years after the Big Bang. These are clustered in arrangements similar to modern galaxies. They're typically less developed than modern galaxies. So they haven't quite settled down to the same sort of structure that the galaxies around us are, but they're still all the same quite large clusters of stars. One of the big questions, of course, is how do these galaxies form so quickly after the cosmic microwave background radiation, after that era? It's only about 1 billion years, and we've certainly got this massive clustering. What I should say is that actually, I should go back to. So basically, this really represents the fainter. Basically, everything in this picture is a galaxy, with the exception perhaps of one or two of the very. Correct. There are a couple of stars. That one there's a star. It's got the little what you call it, the sun. And that would be relatively close to the image. But most of the objects, particularly the fainter objects here, are all galaxies. And the fainter objects are galaxies really getting back to about 1 billion years ago, 1 billion years after the Big Bang. So they're looking at that photo, we are actually looking at some of the very earliest galaxies.
The data on the PV6, the big galaxies on each. They're all orientated in random directions. So something like here, which looks a very nice whirlpool, probably looking at end on. This one here, we're looking at that's on the axis is out this way, and we're looking edge on. Yeah, and that's typical of a lot of those photos where you've got a little galaxies in them. They're pointing in random directions. I'll skip back to where I was. Okay, you've probably seen one of these pictures before. It's essentially an attempt to try and spell out the age of the universe across a simple diagram. So we've got the original Big Bang here. Inflation occurred, there was a very rapid expansion. You can see there the cosmic microwave era there, the dark era. First stars forming, then galaxies form and gradually take shape. One of the things that happens after about 5 or 6 billion years is that initially the expansion is slowing down, but then suddenly it starts to accelerate again. That's the next thing I'll talk about. In 1998, a couple of teams led respectively by Brian Smith and Saul Perlmutter discovered that the universe in fact is not slowing down, but is in fact accelerating. Expansion is accelerating. Here's a picture of Brian. They proved this discovery by looking at Type 1a supernova. In fact, Brian Schroeder is saying that when he started looking at these supernova, he was expecting to measure the slowing down of the expansion of the universe. And he was getting the opposite result. He was getting worried, and the more he looked at it, the more he realised that in fact that was correct. And what was interesting was both teams were doing similar work at the same time independently, and they both realised they were looking at the same thing, and very hastily they both went to press to make sure that they didn't get gazumped by the other one. But so they both awarded the Nobel Prize at the same time because they did work independently and they did publish it further close together. Okay, so the acceleration is caused by what we refer to as dark energy. But it's also in the past been referred to as the cosmological constant. It was first proposed by Einstein, who first proposed it and then changed his mind. Okay, what is dark energy? We don't know. We've got some ideas of what it might be, but we certainly we don't know exactly how much there is and exactly why it's there and so forth. The best candidate is what's called the vacuum energy of space. This is something that's predicted by quantum mechanics, and unfortunately the value that quantum mechanics predicts for it is out by 120 orders of magnitude. When they first realised that perhaps the vacuum energy of space might be the cosmological constant, and they did the numbers, they said, not quite. There were various attempts to explain the difference, but unsuccessful. Okay. So if we look at the universe in the modern era, it's a bit of a diagram of what part of the universe is actually made up of what. Only 5% of the modern universe is built from known matter. 70% is believed to be dark energy. 25% is believed to be what's referred to as strange dark matter. There's a few other different terms for it, but so looking at our little diagram here, is there a pointer somewhere? Sometimes my cursor disappears when I most need it. Otherwise, we'll grab it again. Okay, so dark energy is this. Dark energy is this. I don't want to it easy to handle.
Oh, that's what I kind of like the analog one. The speaker has a choice now.
Okay. So this area here is the percentage of the universe that's dark energy. This is what we sometimes call strange dark matter. It's still matter, but it's not made from protons and neutrons, basically. All the rest is made from ordinary matter. About 4% is just hydrogen and helium that was created in the Big Bang, that hasn't yet been incorporated into stars, and is floating around in large clouds, basically. Now you'll notice the little diagram on the left doesn't add up to 1%, but obviously these figures are rounded. In fact, there's probably should be a plus and minus after this anyway. And You'll notice in different books they actually quote slightly different figures. Some will say 72% or 73%, and some will also say 69%. Don't worry too much about that, but it is around about 70%. It's around about 25%. The other thing is that the ratio between this one here and this one here is about 5 to 1. That's fairly well established as well. Okay. So 0.5% of stars. So when you look up in the night sky, all the stars you can see and all the stars you don't see add up to 0.5% of the universe. 0.3% of neutrinos, which you don't see. And these are heavy elements, which probably includes most of us. So that's the balance in the modern era.
If they think that the acceleration of the universe is being caused by dark energy, do they think that that means that dark energy is increasing?
It is, yes.
So it may get bigger and bigger or more.
It will, yeah. Okay. I'll come back to it in a minute, but the composition of the universe is based on the following evidence: the cosmic microwave background radiation. That's certainly given us part of the information. Type 1a supernova data, as I mentioned before, and the other one is the clustering of galaxies. Each of these contributes to the numbers that go into those things. But this is a fairly early graph, and it probably isn't relevant today, but I think this was published about 2000. But what I like about this graph is that it actually shows how the different elements come into play. This green area here represents the microwave background. So it's predicting a range of numbers that lie in the area there. This one here, the dark blue, if you plot all the numbers from the clustering of galaxies that lie in this area. And the supernova data lies in this light blue one. And I notice there's only a small area inside that red circle that they intersect. So that's the evidence that points back to that previous graph. That line there represents the flat universe, and that point there was the original idea of the universe, which is basically no cosmological constant, no dark energy, and just enough mass to make the universe flat. Actually, am I wrong there? I might be wrong there. I'll take that back. Sorry, that point there, sorry. But here, basically, is 30% mass, 70% dark energy in the middle of that triangle, middle of that circle, sorry. I haven't actually seen an updated version of that graph, unfortunately, so that's one of the reasons I had to go that far to do it. Okay, as the universe expands, the density of ordinary matter and dark matter reduces. Okay, so basically we're saying that the actual quantity of them remains the same, but obviously as it expands, the density gets less. Matter has not been created or destroyed. The density of dark energy is remaining the same. This leads to dark energy increasing its fraction of the total. So as time goes on, dark energy will become greater. As dark energy increases that fraction, acceleration will increase further again. So the inevitable scenario is that the universe will just continue to expand ever and ever faster. Unless dark energy does a U-turn and something I'm really there. Okay, I'll just have a quick look at, just for fun of it, some of the things that are being built and these are basically objects, and a lot of the rationale for targeting these is to look at this early era. First one is the James Webb Telescope, which is Hubble's replacement. Hopefully be launched in 2018. L2 there is what's called the Lagrange point, and it's a stable point around the Sun, and it gets dragged around by the Earth. And it's got a head segmented mirror with an area of about 25 metres squared. And up in space, that's an enormous telescope. It's 5.5 times the collecting area of Hubble. Giant Magellan Telescope, we've actually had a talk on that, I think, not too long ago. It's supposed to be in operation in 2020 in the high desert in Chile. It's built at the site of the current Magellan telescopes, which I think are 4 telescopes of about 8 metres in diameter. Seven mirrors, 8.4 metres in diameter, total effective diameter about 24 metres. It's got adaptive optics on the secondary, not on the primary. The primary is fixed. $30-metre telescope, supposed to be in operation in 2021. I believe all these telescopes are funded fully. This is going to be Mauna Kea Observatory in Hawaii, right next to Keck. This one's got 492 mirrors, 30 actually says 30 metres squared, should be 30 metre diameter. The European Extremely Large Telescope. This used to be called the Overwhelming Large Telescope. It was originally planned to be 100 metres in diameter, but they changed their mind, and some bright spark said it was now once was large. But early 2020s, it's going to be in Chile again, and it's going to be very close to the Very Large Telescope. 398 hexagonal mirrors and a total diameter of 39.3 metres. It's down 3 metres from where it was a couple of years ago, but all the same, still it's the largest one that's currently being built. It's an enormous 39 metre telescope. This is an interesting one, Large Synoptic Survey Telescope, operation in 2021, also in Chile, site of Gemini South. It's got an 8-metre mirror, but this is a wide field telescope. It's got a field of view of 3.5 degrees with an 8 metre primary mirror. And the last one for Ken's benefit. Square kilometre array, operation between 2020 and 2024, stage 1 and stage 2, in Western Australia and South Africa. Thousands of antennas, total collecting area of 1 square kilometre. This little picture here is the density of, this is basically the centre of the detector. About half the antennas are within 5 kilometres of the centre. And the rest are spread out over in sort of getting further apart as you go out, up spread out over a diameter of about 6,000 kilometres. Which basically means it covers the whole of Australia and New Zealand. But there's only 1 or 2 telescopes out in that distance. And from what I can understand as well, looking at their site, is that they're going to build 2 separate telescopes, one in Australia and one in South Africa, and then join them together somehow. And the head office is in England. The big telescopes over there. Half located 5 kilometres from the centre.
Getting to hurry up so some of us can see it as well.
Yeah, well, that's right. With only 5% of the universe understood, there's so much we've yet to discover. These will help us to find the answers. New theories are being developed all the time. Some questions require even larger telescopes, like the 100-metre overwhelmingly large. And that's the end. Yeah.